Everybody, so we are the answer session for C5 LICS 2020, and we will start with a paper by Salomon Zickert and Javier Esparza on efficient normalization procedure for linear temporal logic and very weak alternating automata too. Please, okay. Salomon, if you can present in 2 minutes main results.
Okay, yes. So let me give you the 1 or 2 minute version of our paper. So before I talk about our results, let me talk about some previous results by Chang, Mana, and Pinelli from '92. So what they have shown is that if you take an LTL formula, and here you have a tree, and just focus here in the tree of the formula on the operators globally, release, and weak until, that's the blue dots, and then on the finally, until, and strong release, that's the red dots. So then the formula will have that shape, and you have red dots and blue dots and the other operators we're not interested in. And this results tells us that you can rewrite this in some kind of disjunctive normal form, such that on every path from the top to the bottom, you will see at most one switch. So you will one path either see a red dot and then blue, or on the other hand, you will see blue and then red. So while this is very interesting and the idea of this normal form sparked a lot of further work, so there are synthesis procedures and model checking procedures taking subsets of this normal form, in practice they haven't been done that much because the construction itself is non-elementary. And basically our contribution here is to get an exponential construction. So this is the first result, and this is the main result we're going to present in the video. So what is that good for? And we present one application, that's translation to deterministic Rabin automata. So going from that specific normal form, which we call delta 2 because you just have one switch, there is corresponding a class of very weak alternating automata where you can translate linearly to. And that looks very similar to the form here over here. So you have either on the path through your automaton, you either have in the beginning rejecting states and then you just see accepting states, or you start in accepting states and once you leave the accepting states, you just see rejecting states. And from these automata, there's a very simple determinization construction such that you obtain Ko-Büchi and Büchi automata deterministic ones. And then you can just build, following that structure, following the DNF, you can build a deterministic Rabin automaton of that. So in total, you would get a triple exponential construction, but if you look a bit closer to it, you will in fact get a double exponential construction. So if you look at the constants and the numbers very carefully. And that's basically the context where our work is put in. Let me say here that this is just one application. So of course you can go from the special type of automata to other classes. You can build non-deterministic Büchi automata from that, or you can build LDBAs and so on. So the main contribution is exactly that syntactic exponential rewrite system. Thank you very much.
Thank you. So maybe we can start with a question from Noreen because she put it on Slack before.
Yes, yes.
So if you've seen this already, maybe I don't ask them, Noreen, to repeat it. Maybe you can just reformulate it and reply.
Yes. So the question was basically, what is the idea of this determinization construction? And the idea is the following. So take one of these special weak automata. So we take the ones that start with rejecting states. And then you have here rejecting SCC, for example, and here you have an accepting SCC. And I'm not going to write down what kind of branching mode we have. So this is a mixture of universal and non-deterministic branching. And this has to be also accepting. So we know that a word is accepted by this automaton if and only if there is a rundex, an unfolding. So here we read the word. And then we build such a DAG. And these are the states from over here. And this goes on and on to infinity. And we say the word is accepted if and only there are infinitely many accepting states on each branch. So for example, here and maybe here. So the important thing is now, since we have the syntactic restriction, is that once we reach an accepting state, all the states going here are accepting. Thus, in every accepting run, there is a run deck such that here there is a level, and from now on, here's everything is accepting. So basically, what the deterministic automaton does, in this case, the deterministic Kobuchi word automaton, is track all possible run decks, and once you see a level that only contains accepting states, track that particular run deck and see if this is a complete run deck, so if it goes for forever, or at some point it stops. And if it stops, then we know this is not good, because then our candidate was chosen wrong, and then you pick the next one from some kind of queue structure. And there's an argument that you never miss something.
Thank you. Are there any other questions? It would be nice if you post them to chat, and then you can pick your mic and just ask. Mikołaj has a question. Please switch on your mic and.
Thank you. So there is a construction you can which goes from using omega semigroup. So if you have an LTL formula, you can construct an omega semigroup. And then there is from an omega semigroup you can sort of construct like an automaton, or you can. I'll put it this way: using omega semigroups, you can prove determinization of Büchi automata. So it's an alternative with respect to usual determinization constructions. And I was wondering if you did the same construction, but did it inside LTL, maybe you could get a similar result to the one that you have. I'm not sure if it will be doubly exponential.
So in fact, the normalization construction itself is exponential. And so you're thinking of the Krohn-Roth decompositions, if you would look at from the automata perspective, right?
No, I was thinking about a different construction where.
Okay, then I'm not sure.
Yes, but it's just speculative. I mean, your description somehow seems similar. I can try to send you a link.
That would be perfect. Yes.
It could be related. Maybe not. Thank you.
One thing I can add here is, so there is the result that improved. There's another result that improved the non-elementary bound. And that goes through the Krohn-Roth decomposition. But the difference there is the resulting formula will be GF and something FG something. So that's going to be this junction. But this is going to be past LTL in here. So there is a result that does that. And this is known to be, if I'm not mistaken, known to be triple exponential. But we looked at that construction and we haven't seen any way to rewrite it into something that talks about future LTL. And this necessarily depends on being able to look at the past.
Thank you. So the construction I have in mind, I don't see why it would need past LTL, but because it says something like infinitely many infixes, finite infixes of a given form. And now I'm not sure how you would formalize infinitely many infixes of a given form, so that may or may not require past LTL. That would require some, I guess, looking at attention. I try to send you a link, but it's just speculative. Yeah. It's more like a question. Yeah.
No, yeah. Okay. So I would be happy to see the reference, because actually we're looking at related questions now, and some of our techniques are not good enough to continue that. So I would be happy to hear the reference.
Thank you.
Thanks.
Thank you. So I would suggest that I see there are more questions, but I suggest to move to second paper, and if you have time at the end, we can move back and pose other questions. So please, Rasmus, it's your time to present 2 minutes.
Yes.
Your results.
Yes. So I'm talking about one-clock price-time games, and we show that a PSPACE-hard. So roughly speaking, what are these games? Well, you would take dice as shortest path problem, make it into a 2-player game, and then you give the players the option of waiting what starts the time stays between 0 and 1. And the cost then depends on on the state as in how much it costs to wait. And the result is basically that this one clock price time games, and they have values that depends on when you start in a state and which state you start in. So, for instance, if you took this example here, this is all the cost functions for this example. So, for instance, the top left one, the one number 3, it costs 3 to wait in, and has the function to the left of it as the cost function. The sort of, to my mind, the important part of them are this number of line pieces making up this output functions. And what we show is that that doesn't look nice. I'm not sure what to do about that one, but we can generate a lower bound construction that ensures that we have exponentially many line pieces. And we then use that to make a P-space hardness result. I think that was it. Questions?
Yes. So David, maybe you want to put your question online. Hello.
Okay, I mean,
no, so this is for it was for Reino. Sorry, Reino, you had a question.
Yeah, I can read it out. So
yes,
the question is from Slack by David Jansen. Would it make sense to allow negative holding rates for states or negative cost for edges? Does that make the problem more difficult?
I haven't really seen anything that makes it more difficult. There is a slight amount of more difficulty in that, even in the version without time, you might have that you don't get simple paths anymore. Right now, if we ignore the time part of it, then you sort of get a simple path to the system similar to the Dijkstra's problem. But if you allow negative cost and edges, well, similar to Dijkstra, you might sort of want to run around in a cycle and get infinite negative cost and then want to go afterwards. So this is sort of I expect that will not be present in a positive version. I don't really know if it makes it harder though. There are a few papers trying to work on it, and they end up roughly with the same kind of result as we do for only this non-negative version.
Okay, thanks. Any other questions? Then I have a question in the meantime. You have a binary encodings of weights, which is helpful in this setting. You mentioned the problem of unary encodings. So this would kind of prevent you to construct this gadget that has a lot of event points, no? This is, so yes. It's just, like there is no, do you have any clue for what to do with unary encoding?
We managed to show something, but it wasn't as an, if you have a constant number of different weights, as in there's numbers on the states, the cost of waiting, then you end up with a polynomial time algorithm of a previous result. But basically, if you have a constant number of different weights, then you can do it in polynomial time if you have unary encoding of weights.
Sorry. Thank you.
Okay.
Any more questions? Then another question I have. So essentially, there is one gadget that solves, because you also present many different subcases, like bounding the size of the graph, etc. So there's essentially one gadget that is the main.
Yeah, I was trying to show it, but unfortunately it got messed up at some point.
Yeah, this gadget that makes a lot of event points, as you call them. Yes. So this is the main tool that makes it.
It is, yes, and because it's so simple, it belongs to extremely many special cases, and therefore extremely many special cases are hard as well.
Okay, and
just a question about timer. Why do you have time in 0, 1? Is it could you have more, or is just
Yes, I'm presenting as a 0-1 part only because I showed in a previous paper on this stuff like 7-8 years ago that you can reduce to the case where the time is only in 0-1 in polynomial time. So is polynomial time equivalent to the general case where you have general time, and you can sort of say that you may only go to this edges between, say, time 5 and time 10.
Nice.
And you may also sort of reset edges along the way. But again, all of those things can be removed in polynomial time.
Okay.
And so you also recall this old problem of 2 clock timed games.
Sure.
So one way to attack this would be to try to code kind of your gadget with 2 clocks, like having infinite splitting, number of split events or things like this. So
yeah,
how you relate this?
We tried to think of it briefly, but really didn't get anywhere. I mean, it's not a new thing that the 2 clock version is PSPACE-hard. It's already the case for the 2 clock version of just the invisibility part. I think the 1-player version. So I'm sure also many other special cases of the 2-player version is PSPACE-hard. But yeah, we tried to do something with this, as in try to encode more and more stuff into the second variable, but really couldn't get anywhere.
Okay, thanks. Are there any more questions on the channels? No, I think it's fine. So thank you very much for a moment. If there are more questions, then come at the end. And then let's go to the third talk. Mikołaj Bojańczyk. Mikołaj Bojańczyk will present 2 minutes on extensions of omega regular languages.
Should I start now?
Yes.
Hello. So this is joint work together with Edon Kelmendi, currently in Oxford, Rafał Stefański in Warsaw, and Georg Ceche at NPI. This is a one theorem paper. So here's the theorem. It says that if you take a language of omega regular words, which is not omega regular, so it's not recognized by a Büchi automaton, for example, and it has a neutral letter. So a neutral letter means that you take a word and you eliminate the neutral letter, you add it infinitely often or finitely often, it does not affect membership in the language. Under these assumptions, if you add if you extend MSO with this language, I can explain how, then the resulting logic is undecidable. So it means that you cannot go beyond MSO under the assumption of neutral letters and still be decidable. That's the political interpretation. When I say MSO plus L, I mean you have you add to MSO a predicate which inputs a word and tells you if that word belongs to the language L. And by saying a predicate inputs a word, I mean you can view an omega word as a tuple of sets, one for each letter, which says on which positions the word has a given letter. So that's the theorem, and it's meant to say that you cannot extend MSO and remain decidable in a robust way. And in the proof, we use a logic MSO plus U, which is an unboundedness logic that was considered in the last decade and shown undecidable. And we show that if you extend MSO with any non-omega regular language, then you necessarily get MSO plus U, and therefore you are undecidable. Thank you.
Thanks. So let us start with a question from Andrea. Andrea, maybe you can post the question yourself.
Yes. So there's a question which says that this language L with a neutral letter is a bit counterintuitive, and the question is, can I give some interesting properties that my language MSO plus L can represent, which cannot be done with omega regular languages? Now, to be honest, I'm a bit unsure what this question means. So if maybe Andrea is
Andrea, yes,
is around.
Andrea.
The thing that confuses me is that we are not considering one logic MSO plus L, but it is a family of logics for every choice of language L. You take any language, for example, words where the set of omega words where every occurrence of the letter A is on a square numbered position. You add a neutral letter, so you can say after removing the neutral letter, every appearance of A is in a square numbered position. This is an example of an language of omega words, which is not omega regular and has a neutral letter. You add this language to MSO and you become undecidable. And the theorem says that no matter how you choose your language, it's going to be undecidable. I'm not sure if I can respond better to this question, but I'd be happy to try.
Okay, thanks. Then Anka maybe can pose her question.
Yeah, so maybe I can ask another question first. So why the neutral letter? So can you replace it by something else? So what's the reason for the neutral letter?
So the neutral letter, well, the theorem would be false without this assumption. So there exist choices of L which are not omega regular and do not have a neutral letter, such that MSO plus L is decidable. And the reason is as follows. The extensions that we consider are by a second order predicate, which inputs a set and says yes or no. Another form of extensions of MSO would be by a first order predicate. So you input a property, say, of positions, for example, whether or not a position is square or prime. And then you ask if it's decidable. And now this has been studied for like 60 years. And there are known examples of first order unary predicates, which can be added to MSO and retain decidability. For example, in a paper by Rabin from early 60s, I don't know, whether or not a position is a square number, or even subject to some number theoretic assumptions, whether or not a position is a prime number. So these unary first order predicates can be added and MSO is decidable, becomes decidable. And unary first order unary predicates can be represented as second order unary predicates in a natural way. So if you remove the assumption on neutral letters, you do not get a clean dichotomy like we do.
Okay, so, and for instance, these primes cannot be padded with a neutral letter. Yeah, okay, I see. Yes. So actually my question was about, I mean, in your video, you were saying something about the right congruence, that you cannot use it. And then you are going very fast to the game that translates, so it reduces MSO plus U to MSO plus L. Could you use, for instance, Arnold's syntactic congruence to simplify the game?
Thank you for asking. Well, the answer is no. So there is no canonical congruence that we could. So by canonical, so the Arnold congruence is it's a unique. So for every language you get one Arnold congruence. So in this sense, it's canonical, and there is no. It's definitely the Arnold congruence doesn't work. So for example, if you take the unboundedness and you view it as a language U, it's going to have 3 equivalence classes with respect to Arnold congruence. Mm-hmm. And nevertheless, the language itself leads to an undecidable logic. So Arnold congruence, and I think any canonical congruence will not work. So that's why we need to work much harder than in the case of finite words, where you can just use the canonical Michael-Nerodi equivalence relation, either two-sided, one-sided, or yeah. So that's why these omega words are much more subtle, and we need to work harder for that.
Thanks.
Thank you very much.
I see that Javier raised his hand. Maybe he wants to ask a question online.
No, because the question was essentially Anka's. It was the same question. You said that the theorem can be interpreted as any robust extension of MSO will be undecidable, but why is this specific neutral letter something that is linked to robustness, right? It's not.
So maybe I can, since the question was asked again, I can give another answer. So an inspiration for this work was a previous theorem proved by Georg Dietrich Kuske and Markus Lore, from what I remember. And there it was not phrased using neutral letters, but it was phrased as full trios. So our inspirational theorem said that if you take a class of languages which is closed under images of rational transductions and Boolean combinations, then that class is either the regular languages or it is undecidable. So you could, our main result can also be phrased in this language. So you will not have the neutral letter. It will be if you take a class of omega languages, which is closed under Boolean combinations and which is closed under images with respect to omega rational transductions, then it is necessarily going to be undecidable. And here, an omega rational transduction, as is the case for rational transductions for rational relations for finite words, it allows you to, the automaton can insert letters. It's not letter to letter. So the fact that a rational relation can insert letters on the output or on the input because it's metric, or delete letters, is what corresponds to our neutral letter assumption.
Okay, I like that one better.
Thanks. And Rafael wanted to ask a question. It will be the last
just to
one.
be sure, we have an algorithm that for all L, if L does not satisfy the condition, that will decide MSO plus L.
Excuse me.
If we are given an L that does not satisfy the conditions,
yes.
Do we have an algorithm to decide MSO plus L? So the reverse of what is here.
No, I don't think we have such a neutral letter. We say if there is no neutral letter, then we do not make any claims about MSO plus L. It could be decidable, could be undecidable.
Okay, it is not an equivalence. Okay, I see.
But if it does have a neutral letter, under the assumption of having a neutral letter, then either it is omega regular and then MSO plus L is decidable for the usual reasons, or it is not omega regular and then by our results it's not decidable.
I see. Interesting.
So
Thanks.
I think a full classification is beyond the scope of
humanity.
No.
Good. So we'll move to the next paper, and this will be Szymon Toruńczyk, who will be presenting their work on register automata with Extrema constraints. Please, Szymon, if you can give 2 minutes.
Okay. Hello.
Summary.
Can you hear me and see my talk?
Yes.
Okay. I just wanted to mention that the video, slides, and paper are available at this website. Due to our negligence, they're not available from the LICS website. So if you want to see them, then please visit this website. You're welcome to do so. Let me start from phrasing the 2 main results. So, the main result says that the satisfiability problem for first order logic with 2 variables and 2 linear orders is decidable. So this means that we're considering the following decision problem. We input a first order sentence, phi, which uses 2 variables, say x and y, but it can reuse those variables many times. And 2 binary relations, less than 1 and less than 2. And the question is to decide whether phi has a model in which both these relations are linear orders. So that's the question. And we're asking about an arbitrary model, finite or infinite. And we show that this problem is decidable. So for the finite satisfiability case, this was shown decidable by Schwentik and Zoyma. And we do the general case. So they left this as a question, whether you can do the general case, and this is what we do here. And as a tool, we prove the following result, which talks about register automata, which we call tree-register automata with Extrema constraints. And these automata, they process infinite trees, which are labeled by values from which are real numbers, and the automata are equipped with a finite number of registers, and those registers can store those real numbers. And as the automaton processes the tree, and at each node of the tree, the automaton can access the supremum or the infimum of the register values in the subtree rooted at the current node. So this is why we have extrema constraints. So you can compare a given register value to the supremum or the infimum of some register values in the subtree of the current node. So we proved that these automata have decidable emptiness, and theorem we then proved theorem 1 by reducing it to theorem 2. So there's a reduction which reduces the satisfiability problem for the two variable logic with two linear orders to the emptiness of tree register automata. And I just wanted to show you very briefly the idea how this reduction works in the case of finite satisfiability, because the idea is very simple. And well, this reduction I will just show you now will work, can be used to reprove the result of Schwentik and Zäumer to prove finite satisfiability is decidable. And the idea is that if you have a structure with two linear orders, then you can view it as a word of elements of pairs, consisting of pairs. The first coordinate of the pair encodes the color of the current node. So you process the nodes from left to right with respect to the first order. And then for each node, you have an arbitrarily, well, you assign values increasingly to the nodes, increasingly with respect to the second order, and then you process the word from left to right, and you just write the elements with their values, so the color and the value. And this is how you encode a structure with two linear orders as a word, and using this encoding, it's not difficult to encode a first order formula with two variables, well, in Scott normal form. This is a certain normal form which you can achieve using register automata, which can access the minimum and the maximum of certain values seen to the left and to the right. And this is how you can show that, solve the decidability for the finite case. And you can generalize this. So this reduction is quite flexible, so you can generalize it to infinite models and also to other types of relations. Instead of two linear orders, you can have, for example, one linear order and a tree order and some other things as well. So that's all I wanted to say. Thank you.
Thanks. And I think Gregory has a question exactly on this subject.
Yes, that's correct. So first of all, thank you for your interesting video. And my question is, you argue that first order logic with two variables and a linear and the tree order is decidable. But can you try to give some argument why you can't even have more stronger claims? For example, with a similar reasoning, you extend your argument to first order logic with two variables in two tree orders.
Yeah, okay. So there are multiple undecidability results, and I can't cite them all from the top of my head, but I think this case would lead to undecidability, but I'm not sure at this point.
Yes, I agree, Shimon. Would lead to undecidability.
Thank you. Thank you for the backup. Yeah. Okay.
Yeah, so this is the result by Amaldev Manuel if you're looking for a paper.
Okay, thanks.
Thank you.
Any other questions? I don't see hands
I have a
rising.
question.
Oh, yes, please.
Yeah, so you mentioned in your talk that you can decide emptiness of those three register automata by reduction to three register automata without extrema constraints. So I was just curious in how you get rid of those extrema constraints.
Yeah. So yeah, you can think of, in the basic setup, you can think of the case. Yeah. Okay. So essentially, they are those extrema constraints are represented in a way symbolically. Intuitively, if a register is supposed to store the supremum of some values in the subtree, then you want to find a certain witness that this supremum is obtained. So you want to make sure that there are values which are larger and larger, which surpass any encountered value, and approach this supremum which you're storing in your register currently. So you find certain witnesses which will prove that you are indeed exceeding any value which is encountered in the subtree, so that it's plausible that the value in the register is actually a supremum. It is actually not true that it will really, if this condition is satisfied, then the value is actually a supremum, because it might you might surpass any value encountered in the tree, but still not approach the supremum and be separated from it by a positive distance. But this is, you don't have to worry about this. If this is the only problem, then you can somehow morph the values and cut out some intervals in your domain and make sure that the values actually achieve the supremum. So, so the register automaton, what it does is it makes sure that whenever some value is encountered, then some value later on is some bigger value later on is encountered, and it makes sure that this happens infinitely many times, and that's what it does. And then you test emptiness of this automaton. So it's some sort of symbolic representation of runs which satisfy this extrema constraint. But this symbolic representation doesn't need to satisfy the extrema constraint, but you can convert it to a actual accepting run. I don't know if this helps.
Okay, I get the idea. Thank you.
Thanks. And that's why you need parity conditions and not just Buchy conditions in your automata?
Yeah, well, no, I'm not sure. I'm not sure if this if we really need parity conditions. We can use parity conditions to prove actually stronger statements than the one stated in Theorem 1, where you have some additional predicates. I'm not sure if in this form we actually need parity conditions. I would need to think about it.
Okay, thanks a lot. We'll move to the next talk or next answers. So now it's time for Amina Doumane, who presents the paper First Order 3-to-3 Functions, routed with Mikołaj.
Okay, so hi everyone. So this is a joint work with Mikołaj Bojańczyk, and our main focus in this paper was first order 3-to-3 functions. So this is a well-established class of 3-to-3 transductions, which have a logical characterization and characterization based on automata. So the main result of the paper was to add a third characterization, which is more compositional. So more precisely, we came up with a reasonable set of functions that we call prime functions, and we showed that prime functions generate by composition the whole set of first order 3-to-3 functions. So to get the result, we combined several results about lambda calculus, register automata, temporal logic for trees, etc. So there is a mistake in one of the intermediary results pointed to us by Tito, where we say that normalization of lambda terms is a first order transduction. So actually, this is only true when we restrict to only one variable. So this is not, this doesn't affect the main theorem because we only need this relaxed version. And of course, we will add a notice, a correction online. So I'm going to stop here and I'll be happy to answer your questions.
Thank you. So I think Gregory wants to ask a question.
Yes, okay. So also thank you for this very interesting talk. And I have a very easy question. So at one point you mentioned this term constructor, T sigma, for example. Mm-hmm. Can you explain why there are these dangling edges and what do they correspond to in the real term?
The dangling, actually, if you are in the realm of words, you can combine, a piece of word is a word. But if you are in the realm of trees, to have a compositional framework, if you want to combine trees, you need the trees with dangling edges. So a piece of tree is a tree with dangling edges. And you can plug other trees in the dangling edges. I don't know if you, because for us, a tree is something with the zero array nodes. So you cannot compose trees with each other. But if you have dangling edges, then you can plug a tree in a dangling edge.
So it's kind of a placeholder or variable in a term? Okay.
Yes, yes.
Okay, this makes sense.
Yes.
Well, thank you.
Miko, I wanted to comment or no? Okay. Any other questions?
I have a question.
Yes.
Yeah. So I actually have two questions, but so let me ask the first one. You mentioned some implementation at the end of your talk. So I was wondering what you plan to implement. So,
just to use, for example, to use Haskell types to encode the types of our functions are typed functions. And we can imagine to encode our types in the types of Haskell and encode the functions and play with this.
Okay.
The goal is just to play with it and check that everything is correct, because sometimes when you implement, so the paper is structured in such a way that we say that this function is derivable. So if you have an implementation, you have at least the checking of types.
Okay, so thank you. And so if I'm allowed to ask another question?
Yes.
Okay, so it's also about something you mentioned at the end about polyregular functions. So I see what it means in the case of strings, but so I was wondering in the case of trees whether there is a definition even of what it means to be polyregular.
Probably it is in Mikoai's mind. I don't think he already wrote it down, but we can imagine the generalization of polyregular functions from words to trees. But yeah, I don't think that it is written somewhere.
Okay, thanks.
If I don't see other questions, I can have a question. So there is this, one of the primitive operations or functions is this depth-first traversal that is used to implement evaluation, but is it only used there? So
yes,
it looks to me like evaluation will be more basic primitive. I don't know how to encode it, of course, but so if I had evaluation, this would be fine in the sense that theorem would work.
Yeah, so you are suggesting to replace
to keep just evaluation, yes.
Yes, this is possible, but actually, if you see the automata model, the register automata model, it will pop to you that it's really just lambda calculus. So putting it in the prime functions would be a big simplification, of course.
So essentially, your paper is to say that evaluation can be encoded by this bunch of functions.
So this is one of the main results. evaluation can be decomposed. But there is the other one, which is maybe even more technical, which is this unfolding function,
this
which
is what
we need to decompose also. So yes, basically the result about these two results.
But you don't, for unfolding part, you don't need the depth first search.
No.
Okay. Okay. Thank you.
You're welcome.
Are there any other questions? I don't see any other questions. Then we can go to the last paper of this session. I think it's you, Chen, who present the slides.
It's me, Kishore.
Okay, Kishore. Okay. Hello. So the last presentation will be given by Kishore Yotimura-Rujan, and it's about space-efficient query evaluation for over probabilistic event streams.
Yeah. Hi, can you see the slides?
Yes, yes, it's correct.
Okay. Hi. This is joint work with my advisor Rajiv Alur, another PhD student Yu Chen, and his advisor Sanjeev Khanna at University of Pennsylvania. This is a typical scenario of stream processing where there is a sequence of streams, and at each time point you receive a data item and then you process it and you update the memory in some way. Typically, you want to minimize the space that is required to compute some function f of the entire stream. In this, and these data points are assumed to come from some set 1 to L. In this work, we model uncertainty in this data, what to do if there is, if you only have a probability distribution. So to model that, we assume there's a finite set of labels sigma, and at each time step you receive a distribution alpha I over this set of symbols. And in the end, you want to compute the expected value of some query f on sequences of label sigma 1 to sigma n, where each sigma is sampled independently from the distribution alpha I. And we still require that the space use be sublinear in the length of the stream. So here is the overview of the results in our paper. We consider three main class of queries. The first one is regular languages, where the function f is given by 1 if the string is in your language and 0 otherwise. And the second one is given by additive cost register automaton, which is similar to a DFA, but it also has registers which can be updated linearly, and there are output functions associated with each state. And finally, we consider this model, which introduces a bit of non-linearity in the function, where you have one counter automaton, which can either be incremented or decremented, but decrements don't go below 0. And for the first two classes, we are able to show that we can achieve epsilon approximation of the expected value using space that's roughly a log n over epsilon square. And for the counter automaton case, we have we can show that we can compute this with O tilde root and space. Thanks.
Thanks. I see a question from Moses. Maybe you can pose the question.
Yeah, hi. So I was wondering whether you have thought about extending these results to the sliding window setting. So you still have a probabilistic stream, and you're now only interested in a suffix of length n, and you want to maintain this expected, or an approximation of this expected value f under the, or just over the suffix of length n.
Yeah. So this was something that came up when we were thinking about future work. We still haven't worked on it, but yeah, we thought about it briefly. Yeah.
Okay.
Thank you. Any other questions? Then I may have a question. So your space bound is square root of n how, well, it's kind of different from the classical approach that you have logarithmic space. Is it good enough? How you justify this?
So yeah, we were working on lower bounds, and we think that you might actually need root n space for this kind of setting. So so that's one reason, is that, you know, even for the simple case where there's a single state, and then you just have this random variable that's hitting 0 and bouncing back. We think that the lower bound should be root n, and we still think it's good enough for most practical applications.
Okay. And the other point you had is that you need n in advance, no, to run your streaming algorithm. That is, you need to kind of have approximation of the length of the stream. Is it true? This is what I.
It's. I mean, yeah. In the paper, we do assume it everywhere, but in stream processing, there's a standard trick that lets you, you know, estimate this n and then double it every time you see more data points, and it works. It will give you the same answer up to some constants.
Yeah, but this is when you have log memory. When you have square root memory, then maybe you are a bit worse with this trick.
Possibly. Yeah, I don't have an answer right now, but I think we did think about this and we thought it will be okay.
Okay, thank you. Do we have any other questions to this paper? If not, then you are welcome to post questions to other papers. We have still a couple of minutes. So I hope all the authors are still there. I can start also if you. So Salomon, you're still there? Yes. Sorry.
So yes, I'm here.
Sorry. So it's about modularity, because you said that it's one of the features of your translation that is modular. But you need to know this, the sets of untils, etc., before you do your processing. So if I increase the sets of untils, what happens?
Yes, so this is one of the problems, basically. If you increase the number of fixed points, then you have to consider more disjuncts. So like the bottleneck is in the beginning where you translate the formula to normal form. Then you have lots of disjuncts you can process in parallel. Answer that your question, or
do you have some trick to make it modular anyway, or?
So you mean modular the resulting automaton in the end, or?
Resulting formula at the end. So what happens if you have a big disjunction over all possible
combinations,
partitions. So once you add more sets, they have final partition, and this formula kind of changes completely.
It could change. I mean,
maybe
it could.
Yeah.
I mean, it does not need to change that much. So, I mean, so if you add more sets, you can keep the one part as lower half where you before set it to false, or you assume that it's not true. But then you have the other set where you have to add more and more components. And of course, if you add more untils, then most of the time the formula that you start with going to change. But of course, if the formula in the beginning is already in the disjunctive normal form, then you can do it modular.
Okay.
So if there is already, like if you on the flat hierarchy would add more, it's fine. But if you go deeper into the tree, then you have a problem.
Okay. So please post questions. If not, then I will post questions because I have plenty. I see Mikołaj there. You want a no? I want to pose a question to you. So I'm talking about this predicate, the extensions of Omega languages paper. so you show more or less that U is the kind of the weakest predicate that you can add, in a sense that everything can reduce to U. Is there a hierarchy, or is everything interreducible? Because there is this nice, very nice argument that you can reduce to U, but
so I would be very happy if U was the weakest, because it would show that U is the best somehow. But I'm not sure. So if you, there's probably a hierarchy, but I don't think it's very fine-grained. I think it has lots of equivalence classes. And the reason is that, well, when I said that the logic is undecidable, there's actually a stronger statement, which says that subject to a certain natural encoding of finite words as infinite words. So the encoding is, you take a finite word, you write it infinitely often, and you're allowed to make finitely many mistakes. Then subject to this encoding, MSO plus L, under the assumptions on L that we use, will contain every decidable language and in fact every language in the arithmetic hierarchy. So that means that if your basic language is somehow in the arithmetic hierarchy, then it's going to be equivalent to U. The only way to be stronger than U is for your basic language to be beyond the arithmetic hierarchy, subject to an encoding of finite words and infinite words. So I think most languages that you would think of would be equivalent to U.
This is complexity argument, but I was thinking about MSO reductions, not Turing reductions.
So in terms of the expressive power of MSO plus L, I think you always get the same thing, except if you start out with a really crazy language that's not even...
Okay, so everything would be...
But subject to the price with respect to MSO reductions, I don't know. One has to take into account that we were dead set on using MSO plus U. So it's not surprising that it's what we use. So maybe somebody with a different background would use a different. But to be honest, I don't see it. I think it could actually be naturally the thing to use.
Okay. Thank you very much. Are there any more questions to any of the speakers?
I have a question.
Yes?
To Mikołaj about the same paper. What about trees? Finite or infinite?
We didn't think very carefully about trees. I think for finite trees, you should get the same result. Maybe Georg would have a comment, but I think with the same proof, you should get the same result. You have to be careful about the kind of rational transductions that you use, but I think you're going to get the same thing. And we didn't think carefully about infinite trees, but I would speculate that our result, that there is the same proof, would probably give the same, would transfer to infinite trees as well. But this is speculative. I don't want to.
Thanks. So if there are no more questions, then thanks to all of you for answers, questions, participation, and see you at next sessions. Bye. Thanks.